Okay, so I started talking about this a little bit at the end of the last part, and then I realized I was going to run out of time. What's weird about this question, number one here in the chapter C, of course, you know the Form C tests are always a little bit outside the box. You're supposed to make up a number of times at bat n and a reasonable non-zero probability of success p. Well, I don't need you to know anything about baseball. They kind of tell you this. They don't tell you what a good number of times at bat n is. I actually just Googled it and kind of tried to find out how many times at bat someone is sort of up in a year. And I don't expect you to do that during the test either. But I looked that up, and I'm going to let n be 600 in a season. Because realize every time you go up to the plate, actually doesn't even count as an at bat. It only counts as an at bat if you don't walk or something like that. All right, where was I? Just got interrupted there. All right, choose a number of times at bat, and oh yeah, I was saying that they don't even always count. Again, baseball specifics you don't need to know, and a reasonable non-zero probability of success P. Oh, I don't know. How about I choose the one you gave me, 0.27? Thank you very much. I'm supposed to draw the distribution, so that's going to be one of these kind of things where you have your little woo, your little wave, and it might not be symmetrical. It might be more like, whoosh, or it might be more like the last couple ones we looked at were like that. Love this undo feature. Actually, I'm not going to do that now. I'll graph it on the calculator. Find the mean and the standard deviation. Well, mean and standard deviation, that should ring a bell a bit. Great. Oh, the other thing is, when I choose n, we're talking about mean and standard deviation, and that sort of hints that you could maybe also use a normal curve for this. Make sure, if we were going to try to use normal curve to approximate a binomial, that both of these things are happening. So I guess you do have to pick your n's and actually I guess your p's and q's too, so that these are bigger than 5. And if I pick an n of 600, I'm really not worried about it. So it's just something that's beyond the table there. If p is 0.27, then q has to be 0.73 because these have to add up to 1. That's the probability of not getting a hit. All right, so then I guess, yeah, mean is just 600 times 27 times 0.27. It's how many of those do you expect to get as hits if it's 27% of 600. 600 times 0.27. That's how many of them should be hits, which is exactly 162. And the standard deviation is the square root of that np times q, which is 0.73, which is this, and then I square root that. It's about 10.87, approximately. Now it says draw a binomial probability distribution. Okay, we can do that. I wonder if the calculator would do it that many times. Let's, oh, you know what? It's going to be crazy to try to fill this in because I'm going to have 600 things in this column, or 601 technically. I don't want to put all those in and do the whole thing. I think I want to try to use the normal to model this because these are high enough. Let's not do that. Let's do the normal and find out what the mean is, find out what the standard deviation is, and draw the normal curve around that. Okay, let's just assume. Let's use normal to approximate it, just because it'll be easier. I don't want to mess around with all this other stuff. So let's just assume it's going to be a normal curve, which is okay to do because of this, and I just got to put the mean and standard deviation in the right place. So the mean should be here at 162. And the standard deviation, which is where the inflection point is, that should be plus or minus 10.87 above or below. So 162 plus that is, well, I can almost do it in my head. It's about 11. So it's close to 173. It's about 11 above. And the standard deviation below is about 11 below. It's about 151. And really, for our purposes, that's good enough. Now, this 162, if that's 162 and that's 151, I don't hit 0 right here. I'm not going to care about that. If you really are bothered by it, fine. And just don't draw an axis. That's fine. This is about all I need for that. Yes, it is actually a binomial distribution. If I needed to find the exact probability of getting, exactly 200 hits or something like that, I might use the binomial PDF. But when n is this high, this is legal to do. This is a huge shortcut to finding the actual binomial distribution. The binomial distribution, because these are all really supposed to be whole numbers of yes, no, did you get that many hits, it would be these little tiny stair-step bars under here. But the tops of them would start to look like this really smooth curve, especially for such a high value for n. All right, 2. A 6. I love this question. A six-sided die that came with a new board game has a visible defect, and you're trying to find out if it's fair. Describe a binomial experiment you might conduct to test whether it is fair. Okay, binomial distribution to figure out if this thing is fair or not. We had a question a couple problems ago about, you've tossed a coin so many times. It was like toss it 14 times and only 2 of them are tails. Is that fair? We could toss this thing. Oh, we just have to make sure it's big enough, really. Like there's a bunch of these tests for is it big enough to be trusted kind of stuff. Let's just make it huge. Why not? Let's Oh, and the probability of each thing is supposed to be 1/6, right? It's a six-sided die, so we have probability of each thing being 1 to 6. Let's say we're going to toss this thing some huge number that's a multiple of 6. 60 should be big enough. We're going to toss it 60 times. We're going to talk about the probability that it is. I guess pick your favorite number. Maybe we should do it for each one. Let's start with, let's count number of, let's call success the number of ones, and then we can redo this for, like, our random variable here is going to be the number of ones that you see on there. So you should expect there to be, if it's fair, you would expect there to be 10 of those, because that's n times p. Probability of rolling a 1, it should be 1/6. So I actually thought about mean before I thought about that, but that times p is going to be 10. Oh, actually, this starts to look like another problem, doesn't it? With exactly 60. That's fine. Standard deviation should be... it says use binomial, so I don't really care about standard deviation. I'm supposed to use binomial. I'm supposed to see... I'm really talking about how to design the experiment. This is starting to look a lot like that earlier problem. I would toss the die a whole bunch of times. I would see how many ones I actually toss. And let's say, I guess at this point it's what if. I can't really describe the experiment and go into actual results. I would just say, we're going to toss, you know what, let me type. Toss the die 60 times and record how many ones show up. Test this total using a binom PDF, and then we'd go how many trials were there, what's the probability of success. That's 1/6, by the way. I'll put spaces in here so it's easier to read. That's 0 point. And I would store that list as L2. Store that list as L2. And then sum L2 from... I'd want to find out, now, is this too many or too little? You know what? I don't even know. I'd have to know the actual results. Then add up the probabilities. I should say do it this way. Test the results against expected probabilities, 10 successes, to see if it is strange beyond a significance level. Just like we did on that other question earlier. Make this look a little bit prettier. Right, so let's say we actually did this, and I found out that it only got to be 1 like 4 times. I would think, okay, 4 is kind of low, and then I'd add the probabilities of 4 or 3 or 2 or 1 and see if that gets to be bigger than whatever my significance level is. And I don't know what that is. I get to make up what it is. The other thing I should say is repeat for other die outcomes. I should see, well, yeah, maybe I'm rolling a fair number of 1s, but I'm not rolling a fair number of 5s. So you should technically do this for each side on the die. This would take forever to do this. But if you were in Vegas, you'd really want to be serious about that. So that's just kind of getting you thinking. That's kind of cool. All right. Equation of the curve graph at the right is this. Well, you're supposed to recognize that is the standard normal. I should type this. Standard normal distribution. Great, because we know things about that. We know things like what the area is and where the inflection point is and what the maximum is. Label the vertical and horizontal scales of the axes. Well, this looks like the inflection point here, like where it starts to twist the other direction. And I bet that's here. And I'm kind of saying right there because, look, that's right over one of these things. So that should be 1 and -1. It looks like these tick marks are at half. Also, this is supposed to be just under, this peak is supposed to be just under 40%. So I'm guessing this means 0.1, 0.2, 0.3 on the tick marks. Very tempting to say that. Then state as many facts as you can about the curve and what it represents. Geez. Let's go ahead and start typing. This curve seems to model the... I'll even use capital letters, make it really official. What else should I say? The area under the curve is 1. The curve is symmetric with respect to the y-axis. The inflection points happen at x equals 1 and negative 1. What else do we know about? The maximum is at x equals 0. Z is approximately equal to 0.3, I think it was 98, dot, dot, dot. Is that all the stuff we knew about it? There is a horizontal asymptote. This is so much better than me writing this out. At y equals 0. So no minimum. Our domain is all real numbers. I can't think of anything else to say. That's like 7 facts. And the probability is, 1. Great. Yeah, I'm on a roll now. All right. This may be the last video, so let's see how far we get. Okay, this is very real life. The average life of a certain type of light bulb is supposed to be 3,000 with a standard deviation of 250. Explain how a consumer interest group might test this. Well, this sounds like sampling and distribution. If you were going to try to check this, you would go out and take a sample of so many and find your average and see how your average stacks up to the real, the actual claim. We had a lot of problems like this where they would give you that. They give you, okay, somebody tried a sample size of so many, and they got this average. How weird is that average? So let's suppose, I'm going to actually make up the fact that we tried this. Suppose we did a sample, and because this is what you would do. You would, let's suppose we had a sample size of n equals, and we got to make sure it's bigger than 30, otherwise it's like not even legit. Say we had a sample of 50 of these, and we got a mean. The mean of our actual field tested sample data. It's supposed to be 3,000. Let's say it was a little bit low. Let's say it was 2,900. And we're saying, whoa, Mr. Light Bulb Manufacturing Corporation, you are lying. They only last 2,900 hours. Looks like it's dripping in red here. So it makes it a little scarier. Okay. So let's say it's 2,900. Is this weird? Like, how crazy is that? Well, it was supposed to be 3,000. The sample distribution is supposed to have a spread of... I say spread, I mean standard deviation. The standard deviation should have been this, which here is 250 over the square root of 50. It was my sample size. So I just need to do a normal CDF and see how weird it was that I got 29. So I'm going to go... 29 is on the low side, so I'm going to check everything up to... So from negative infinity up to 2,900. That's a comma. With a mean of 3,000. And a standard deviation of whatever that is. I'll type that in later. Let's go here and let's do the 250. Whoa. That's not what I wanted. That's not what I wanted yet. Let's do 250 divided by the square root of 50. So this would be the, for any sample size of 50, this would be the expected standard deviation. So 35.35. Something like that. And then let's figure out what this is. Alright, it's normal CDF. I got about a minute left. Life is good. I'm going to stop here tonight for these, and then I'll make some more if these get a lot of hits. How about that? How about that for fairness? Negative infinity to 2,900. Negative infinity to 2,900. I think this is actually going to be not too weird. 2,900 is really not that far after 3,000 at this level. My prediction is. And my standard deviation is that answer. Love doing that. Okay, and it turns out that, well, it's only supposed to happen 0.2% of the time. So yeah, that's really low. I'm not talking percents now, I'm talking actual decimals. So that's pretty weird. They look like a bunch of liars. Yeah, that's less than any kind of significant level we'd probably test. So I'd probably say that's a false claim at 3,000. This is what really happened. Anyway, that's how those simulations work. I'll make a new part if so warranted. See you in class.